And as you saw in the last slide, Cynthia will be available in between breaks on WonderMe to interact with the virtual participant. Before the next session, I have a public service announcement. Today's social event is a lovely boat tour across the Amsterdam canals. It will be approximately 1 hour. Boats start at 8 p.m. sharp, so after the session, we will be making our way. It's a 5-minute walk, so go to the toilet, grab a drink, whatever you need. You need to get a ticket that will be provided by in the registration desk if you want to go, so that we can control sort of who's there and so on. The boats are starting at 8, 8:15, and 8:30. We'll try be accommodating you all, and it will be finished by 9:30. After which, you're all, and I think following today's keynote topic, you're all very welcome to experiment some music and karaoke after, both in Amsterdam and virtually.
Okay, good afternoon, everybody. Without further ado, we'll get on to our first technical session of the afternoon, which is on scalable performance. So we have 3 talks in this session. They're all remote, but 3 very interesting papers from Microsoft, from University of Southern California, and from Osaka University. So we'll start with our first talk, which is local factor models for large-scale inductive recommendation. Okay, over to you.
Oh, am I? Okay, great.
Yep.
Hi, everyone. This is Longqi from Microsoft, and it's definitely amazing to see everyone virtually, and it was definitely also quite an experience to get up and present at 5 a.m. from Seattle here. But hopefully I'll be able to see each other. We'll be able to see each other in person very soon. Anyways, in this presentation, I will talk about our work on kind of developing local factor models for large-scale inductive recommendation. And this is a joint work with my colleagues, Tobias, Schnabel, Paul Bennett, and Susan Dumais from Microsoft. So this work is really motivated by the fact that user preferences are very much locally structured. And when it comes to user-item interactions, users and items typically form co-clusters. So for example, those who are very into hiking may be interested in items related to hiking destinations, equipment, forums, and weather forecasts. And those who live in New York City could be interested in learning about local stores, street fairs, real estate, and other related government resources. And as you can imagine, in a typical information platform, one could have lots of such co-clusters in the joint people and item space. And we argue that leveraging these low clusters is critical for recommendation, not only in terms of accuracy, but also their controllability and interpretability. And to successfully leverage such structures, we argue that we really need to capture 3 of their most important characteristics. So first, as the name suggests, is the co-clustering. And in other words, the user and item subgroups need to be paired with each other. And second is sort of the overlapping nature of these co-clusters, because a user can belong to multiple interest groups, and at the same time, an item can at the same time, serve multiple groups too. And third, very important, large scale, that is, the number of such potential co-clusters on the information platform can be huge. And in the RecSys literature, there's a class of work that sort of focus on capturing such structures. And these models are generally called the local models. So, oops, it looks like the slides doesn't advance. Anyway, yeah. So basically, like this paradigm of typical local models that the product work typically follows is to sort of first conduct a clustering or co-clustering in the joint user and item space, and then train a local model for each co-cluster before aggregate them all together for the item recommendation. And when it comes to the three properties that I discussed earlier, these models are doing very well in capturing the co-cluster nature. And depending on the co-clustering approach that is adopted, they may or may not be able to handle the overlapping between the co-clusters. And a significant pain point, though, is that these models cannot scale because we need to explicitly instantiate a model for each local cluster. And at the same time, because of this, this actually presents significant challenge in terms of memory and online serving costs. And this is also one of the main reason why these models is very difficult to deploy in the production or in the industry systems these days. So in this paper, basically we present an end-to-end local factor model that replaces this kind of traditional two-step paradigm with an end-to-end fully differentiable architecture that can capture all three key aspects. And the model is simple, but very effective and is ready for the large scale platforms. So this is an overview of the structure of our model. Our model basically learns an embedding for each item, which could also be enhanced by explicit content features. And with these item embeddings, there are two main components in the model: an item aggregator that sort of computes the user representation, and a component named differentiable latent co-clustering that conducts the co-clustering, local model training, and aggregation all in one differentiable step. So our item aggregator takes item embedding as inputs and uses a self-attention-based mechanism to build the user representation. And the significant benefit of this compared to learning explicit user embedding is that the model is able to generalize to unseen users and serve under inductive recommendation setting. And with the user and item embeddings, so this module called differentiable latent co-clustering, or DLCC module, basically learns a shared co-cluster embedding for each cluster, and then uses dot product to compute a user and an item's affinity to a co-cluster, respectively. And note that in this case, we'll have one set of user embedding, one set of item embedding, and one set of co-cluster embedding, as opposed to instantiating the full models for each co-cluster as done by the prior work. And at the end, we build a soft counter using sort of the ReLU and the mean sum pooling that capture the user item joint affinity to co-clusters using the separate user and item affinities. And here the joint affinity is high only if both the user and item are highly affiliated to a co-cluster. And in experiments, we find that such joint affinity can be really used to bridge the gap between the co-clusters and the user item sort of preference scores, and really produces great recommendation performance. So comparing our model's costs to baselines that include both the the non-local deep models and local models, the memory and model size requirements is significantly reduced. And at the same time, our model supports fast incremental inference due to our, sort of this kind of coupled design of the attention mechanism and the latent co-clustering. And this is particularly beneficial for online serving situations in the industry setting. And you can check out our paper for more details here. So we conducted extensive experiments on 3 large-scale datasets with varying degree of density. And the datasets range from the search click logs from Microsoft Bing, that is the web dataset, the music listen history from Last.fm, and the movie rating history from MovieLens. And we evaluate our model against both a top K recommendation task and an inductive, and in a sort of inductive and strong generalization setting. And we also conducted a crowdsourcing study where we explicitly evaluate the quality of the detected user item co-clusters. And in terms of the top K recommendation performance, we find that our model significantly outperforms all baseline models, including non-local and local models, and it's able to scale to web scale data set where local models cannot be applied due to out of memory issues. And on smaller data set like MovieLens, our model performs competitively with the baselines. And also, even on data sets that all of the methods can be applied, for example, Last.fm, as I show here, our model achieves significantly better top K recommendation performance with much smaller model size. And this is a very much desired property for medium-sized platforms. So to explicitly evaluate the quality of the detected clusters, we conducted a crowdsourcing study using the web dataset where we asked the crowd workers to identify a randomly selected intruder website to the item subgroups that different algorithm detected. So intuitively, the more coherent the item subgroups are, the easier it is for crowd workers to identify the intruder. So for example, in this case, as I showed in this slide, Bloomlink is clearly an intruder, as the rest of the website are all about camping and outdoors. So our user study also shows that our model produced the most number of non-degenerate co-clusters that are accurate and coherent among all methods. Yeah, I think I'm running out of time, and this is just the end of my presentation. So please check out our paper for more details and send me emails if you have any questions.
Okay, thank you. So as usual, any questions in the audience up to the microphone or questions online in our app here? Let me start with a question. So you talk about overlapping communities, and I think one of the challenges with community finding at large scale is where the boundaries of these communities lie. And when I think about your algorithm, intuitively, I'm thinking about local groups, which might be families, or they might be schools, or they might be organizations. There's lots of different scales. So I wonder how that impacts on your algorithm and whether you need to take into account where the local effects are happening in your data.
This is a great point. I mean, so in our methods, in order to sort of detect such like community of different size and scale, as you said, there's a boundary between communities, and to make it a scale is to not explicitly detect those boundaries in a data set. Instead, you sort of self-assign the affinity between user and the community, or the item to community, in a way that like you don't draw like hard boundaries, but instead there's a soft boundary.
Sure.
So that things are continuous and differentiable that you can learn in a large scale.
But you do have your parameter, which is the number of communities. Is that fixed in your model?
Yeah, that is a hyperparameter.
So do you think that number has to change depending on the data set?
Yeah, so we did try, do the hyperparameter sweeping in 3 data sets of different scale. So yeah, different data set definitely saturate at different a number of communities, and you can imagine, I think one thing that we find is that for larger scale data set, you have to have a larger number of communities typically.
We have one question from the audience here.
Yeah, Bob van der Velde, Dutch Public Broadcasting again. I was kind of wondering, because if I understand it correctly, the community finding is based on user item co-occurrences and not item content features. And I was wondering to what extent you see kind of popularity factors, for instance, where one of the communities will simply be the popular content, which may not have like intrinsically similar characteristics, but it's just the overlapping set of stuff everyone likes, and whether that is something you would want to be able to mitigate in the future.
Yeah, great question. And so first of all, the point about content features, so it's just like in the data set we write in the paper, we don't have content features, so that's why we didn't include it. But in practice, you could easily add the content features as part of that item representation. And for the second part of your question, yes, so indeed, actually in our model, we will always find there's one community that is like the popularity community that captures the popularity of items. So basically, you know, in the model, you can specify, I want to learn 1,000 communities, and there's always one community that rank items based on their popularity, like almost rank items based on their popularity in this user base. So there's definitely popularity bias, and there's actually, you know, one community that explicitly captures that. So I think it will be an interesting question of like, during the serving time, do you want to include that, you know, popularity biased item subgroup to actually improve your recommendation, or like you want to get rid of that subgroup during serving?
Okay, I think we better move on, so we'll thank the speaker again. Thank you. And we'll move on to the next